Hi, this is a project presentation for course EEL 6825 on speaker recognition. My name is Aniruddha Kalya, UFID 391919776. The problem in speaker recognition is to basically identify the speaker using only his voice. In this project, the aim is to build a robust system to perform this task, and we want the system to be robust to different noisy environments. The overview of the presentation is as follows. We start with a brief system description, followed by the components of it, which include voice activity detection and the results of voice activity detection, and that is followed by the feature extraction block, which are then used to model the speaker and then perform a log likelihood ratio test to obtain the results for different speaker ID systems. The system description is as follows. We have a pre-processing block followed by the feature extraction. In the pre-processing, we will implement voice activity detection, and in feature extraction, we obtain MEL frequency Kapstel coefficients. The pattern recognition block builds Gaussian mixture models using these features, and the decision block is used to decide who is the speaker being put under test. So this slide explains the voice activity detection scheme based on spectral entropy measure. So the basic purpose of voice activity detection is to identify the portions of a signal where there is no speech present. So the output of the voice activity detection block would be a signal which contains only speech. And the approach we take here is using the spectral entropy measure. The entropy is defined as given by this equation, which is derived from the Shannon entropy equation. We treat these symbols SI as different frames of the input signal spectrogram. So using rectangular window of 20 milliseconds without providing any overlap, we obtain a time frequency description of the signal, and say y of omega comma t is the time frequency description of the signal. We will sum over different frequencies for a given time index using this equation to obtain the entropy measure, and probability of y of omega t square is defined by the equation shown here, which essentially says how much of a contribution each frequency bin has in a given time frame. So by the definition of spectral entropy, we can easily see that the entropy will be maximum for white noise, which can be intuitively understood as, since white noise has the maximum randomness possible, we get a very high entropy for that. And speech regions correspondingly have lesser randomness because of the structure in them, which results in a lesser entropy. So this information can be used to do a voice activity detection. So if we can come up with a threshold that will detect the entropy values being less than some value, then we can decide those regions to contain speech and the regions which are above a certain threshold to contain no speech. Another important thing to be noticed is that this spectral entropic measure based voice activity detection performs poor in colored noise conditions. In order to avoid this, we employ a whitening filter before performing this voice activity detection. So by this we will ensure that the non-speech regions are fairly white and the threshold based decision will perform reasonably well. These are the results for spectral entropy based VAD. We see that when we have a speech region present in the signal, the entropy in the corresponding region in the corresponding time frame is goes low. So the more the speech present in a given time frame, the lesser is our entropy. So in this region we have speech and we see that the entropy drops down, and when there is no speech we see that the entropy is really high, and so on and so forth. So by having a adaptive thresholding scheme as shown by this black curve, we can decide that those time frames which corresponds to entropy being less than this threshold have speech, and those regions in time which correspond to the entropy values being greater than this threshold correspond to the non-speech portions of the signal. And the decision statistic can be seen here that from this point to this point it has been decided as speech is present. From this point to this point it has been decided by that the speech is present. So this red curve is essentially the decision statistic, and although there are few errors in decision, this method performs fairly well and is uh, has a significantly lower complexity so that it can be implemented in real time. The next block is the feature extraction block. Now once we have extracted the portions of the signal which contain only speech or noisy version of the speech, we can go ahead to capture the features from those speech regions so that we can characterize the speaker. One of the important feature that is used in speech signal processing are the Kepstell features. So the Kepstell transformation essentially helps in converting convolution into summation because it's essentially a homomorphic transformation. And the important thing about Kepstell features is that they represent the articulatory facts created by the vocal tract. So if we can somehow model these model the sample space of these Kepstell features, we can come up with a statistical model for the speaker. So we go ahead and extract these Mel frequency Kepstell coefficients. So the Mel scale is given by this equation, which is essentially a log scale, and this is used because the ear of a human being emulates this logarithmic scale while perceiving audio signals. So we can see that it is less sensitive to slight differences in the amplitude and at high amplitudes than at low amplitudes. This is a simple block diagram that will help us obtain the Kepstell features. We do a pre-emphasis, then window the signal and take the DFT, pass it through the Mel frequency filter bank, then obtain the log of the energy squared, and then perform a DCT operation to get the Mel frequency Kepstell coefficients. Now, if we want to capture any change in the dynamics of the Mel frequency Kepstell coefficients, we can proceed to obtain the derivatives as shown in this block. And this is a curve that illustrates how the Mel scale is essentially logarithmic with frequency. Now the Kepstell feature in noisy environments of performing this Mel frequency Kepstell operation can be improved by having a pre-emphasis block which will help us in improving how we capture the high frequency components, because pre-emphasis will essentially emphasize the high frequency components. We can also perform a Kepstell mean subtraction to remove the effects of any convolution effects of the channel. And as said before, the delta coefficients will capture the dynamics of these Mel frequency Kepstell coefficients. Now the next block in the entire system is modeling the speaker. So once we have these Kepstell coefficients, the next step is to come up with a probabilistic model that will help us in further classification purposes. So we choose to model the speaker using Gaussian mixture components, mainly because Gaussian mixture components are parametric and they have the universality that a finite